Okay, everyone, this is the free response video review of the trimester 1 exam. So hopefully this is helpful. So the first question is talking about the salinity concentration of the ocean. And the key parts here are you're always looking for clues in the question. Percent by mass of salt. So that was the key for this question. So the first part, can you make a general statement about where there's higher salinity versus lower salinity? So there was really a main thing we were looking for, which is that warmer climate gives higher salinity, or closer to the equator gives higher salinity, right? So you're looking for like this part of the picture that has the highest salinity, which is closer to the equator. So we're really looking for one of those two things. Certainly there were some other things you could have said, but you had to support it by the image. A lot of you guys were trying to say that, oh, like closer to the coastline gives you higher salinity. Well, but look up all the way over here and all the way over here, right? That's not supported by the image. The image had to justify what you were saying. So that's what we were looking for there. Calculate the freezing point at the middle of the Atlantic Ocean. A couple issues with the middle of the Atlantic Ocean here that some of you guys had, but that's our ocean here. So we were looking for that kind of dark red spot right in the middle of the Atlantic. So like 3.7 was really the target there. So if it's 3.7% salt, that means that 3.7 out of 100 grams is salt. If you remember our freezing point formula, right? It's based on the molality of the solution, which is moles of solute per kilogram of solvent, just the solvent. So if we want to do this in the most streamlined way possible, I'm going to say that we have 3.7 grams of salt and we have 96.3 grams of water. And then I'm going to do dimensional analysis to work this out. You absolutely could have done two separate dimensional analysis strands here, one to convert to moles and then one to convert to kilograms, and then divided the two. Totally fine, but quickly here, just streamlining this. If I do the denominator first, there's 1,000 grams of water and 1 kilogram of water. That's going to get me my denominator the way I want it, okay? And then we're going to convert 3.7 grams of salt into 1 mole of salt, which is going to be 58.45 grams. And then that's going to give me 0.66 molality. Now I'm going to plug that into my delta T equation. I know that my K value is 1.86, my molality is 0.66, and my I value here is 2. That's key. It's NaCl. It's going to dissociate in water and form an I value of 2. So our delta T is going to be 2.5 degrees Celsius. So our freezing point is going to be negative 2.5 degrees Celsius. Freezing point depression. So if it's going to change by 2.5, it's going to change negatively by 2.5. Okay, sketch a graph. Just a quick little, can you kind of logically put a graph together? So the key points here were, did you put the right things on the right axes? And then do you have the proper relationship? So we were looking for freezing point on the Y and percent salinity on the X. If you got those backwards, then I would encourage you to review some graphing skills. You probably learned this in biology of like independent versus dependent variables, which one goes on which axes. That's sort of just basic graphing knowledge. You should know which one to put on the which axes. The second thing is you should have had a negative slope, okay? You needed to have a negative slope. In a perfect world, this is a linear relationship because delta T, K, M, I, right? In theory, that's a linear relationship there. Now, if you had a non-linear relationship, like kind of bought that, I guess, as long as it was a negative slope, because the I value could contribute a little bit if it's a little bit, not consistent. So I kind of let that slide, but you really should have had a negative slope with the proper axes there. Okay, you take an aspirin consisting of carbon, hydrogen, and oxygen with a total mass of 1 gram. You burn it, you combust it, and you collect 2.2 grams of CO2 and 0.4 grams of water. Calculate the empirical formula. So in order for the empirical formula, you need to have the moles of everything, okay? So we need to convert everything into moles from there. So we're going to be able to get moles of carbon from the carbon dioxide. We're going to be able to get moles of hydrogen from the water. Can't get moles of oxygen directly there because oxygen's in both. But we know that we total had a gram of everything. So if we know how many grams of carbon we had, how many grams of hydrogen we had, we can actually subtract, get grams of oxygen, and then go from there. So I set this up in this method. You may have done it a different way, but this is sort of what made sense to me. So this is the way I'm going to show you here. So 2.20 grams of CO2. I converted that into moles of CO2. And then I said that for every 1 mole of CO2, I got 1 mole of carbon. So it's a 1-to-1 ratio. There's 1 carbon in each CO2. And then I actually decided to stop and solve there because I know I need the number here, moles of carbon. And I got that many moles of carbon. I do need the grams of carbon though, so I actually continued and said that there's 12.01 grams of carbon in 1 mole, and then that's 0.6004 grams of carbon. So part of why I stopped to solve here was because I knew I was going to need this number eventually, so why not stop and solve and then go from there? But you could have done it in a different order, totally fine. So then I went to the water, grams of water, and did the same thing. 1 mole of water is 18.02 grams. Then in this case, there's 2 hydrogens for every 1 water. So that was a key point there. Again, stop to solve and got that many moles of H. But I know I need to keep going because I need the grams as well. So there's 1.01 grams of hydrogen in 1 mole. And that gives me the same grams of hydrogen. So now I have grams of C, grams of H, and I know that I have 1 gram total. So I'm going to actually subtract 0.6 grams of carbon, 0.0444 grams of hydrogen, and that's going to give me 0.353 or 3552 grams of oxygen. And then I'm going to convert that into moles. Oops. 16 grams of oxygen into moles, and that's going to be 0.0222 moles of oxygen. So now I have my moles of everything, and I can create a ratio for that. So I'm just going to actually scroll down just because I'm running out of room here. Actually, I could just do it here. So we have 0.04999 of carbon, 0.0444 of hydrogen, 0.0222 of oxygen. So remember, the trick is to divide them all by the smallest number. So if I do that, I get 2.25, I get 2, and I get 1. So this is where it gets a little tricky. The 0.25 here, this is actually outside of the significance of the measurement. You can't round that. 0.25 out of 2.25 is a significant amount. And so that's too much to round. So what you really should do is try to get all of these into a whole number. So 0.25, if we multiply by 4, would get us to a round number. So if we times this whole thing by 4, we get 984. And so the best answer here was C9, H8, N4 for your empirical formula. So that was the best answer there. Then you can add up the molar mass of this. The molar mass of this is actually within that range that they give you. So this is also the molecular formula. So it's actually both the empirical and the molecular formula there. Then if we write out the combustion equation, it should be reacting with oxygen to give you CO2 and water, and then you just need to balance. So we should have 4 there, and then that would mean we need 8 oxygens there. So that's the balance equation for that one. Okay. For this one, this is really similar to a couple of the labs that we did. So you're going to use Beer's law here. So a student dissolves this entire sample in water, and they measure the absorbance, and they determine it to be 0.3. Determine the concentration. Well, this is just using the graph. I'm going to go 0.3. I'm going to go over to my graph, and I'm going to go down, and I'm going to say that 0.15 molarity is the concentration of the Cu+2 ion, okay? Or the CO4. It doesn't really matter. It's the same concentration. So 0.15 was probably the best answer based on the graph. Then it's calculate the number of moles. So 0.15 is moles per liter. So you're going to multiply by the volume of solution. They tell you it is 100, so it's 0.100 liters, and that's going to give you 0.015 moles of copper sulfate. Okay? Okay, last part. In addition to the number of moles of this, what other info would you need in order to calculate the mass percent? So the best answer here was that you're going to need the total mass of the substance with the impurity. So in order to get to percent, you need the total, right? So you need the total mass there. Okay? Now, a particle drawing here of the ion, and you had to draw 2 water molecules in the proper orientation. Remember, water here, this is the O, these are the H's. Water is polar, so the hydrogens are going to be more likely positive, the oxygen more likely negative. And so you should have drawn 2 water molecules in this orientation. In other words, you had to show the negative oxygen facing the copper ion in order to get full credit. Okay, the net ionic equation. Remember the net ionic equation. Anything that changes quantity, state of matter, or sort of like amount, right? Like charge. You have to show that in the net ionic equation. If it changes from the left to the right, it has to be present. So E changes, H changes. The only thing that doesn't change is Br. So Br is the spectator ion here. So you must say 2E solid plus 2H plus aqueous gives you 2E plus aqueous and hydrogen gas. To get full credit on the AP, you must include states of matter and quantities and all that good stuff. So you have to have it just like I wrote it out here. Next one. Is E being oxidized or reduced justify in terms of oxidation numbers? So we're gonna say oxidized. Always a good idea on the AP. If they ask you a question like, is it this or this? Lead your answer with the word. Oxidized, period. That's the answer. Now I justify. Okay? The oxidation number of E goes from 0, or in other words, its elemental state, to +1. So it lost electrons. That's the key. Okay? Okay, so now we're going to look at some mock data. Here's some data from 3 trials. Student claims that HBr is the limiting reactant in trial 1. Do you agree or disagree? Justify your answer with the information on the table. Again, you should lead your answer with either agree or disagree. So I'm going to say disagree, period. Now I'm going to justify, okay? So there's a bunch of things you could say here, but, okay, in trial 1, right, if you notice here, okay, HBr is constant, but the moles of E are increased, okay? Which creates more product, meaning there's plenty of HBr available to react, so it is in excess, okay? So what we mean by that is, okay, and there's a couple ways you could explain that, okay, is, and they give you some input in the intro as well that you can use, but you're really looking at the trial data here, okay? Okay. So you're saying HBr remains constant, okay? But E changes, creating more product. Okay? So if HBr is constant, but more product is being formed, that's a result of the fact that there's more E. So in other words, E must be the limiting reactant because it's actually impacting the product. Okay? So it means there's plenty of HBr available to react because when you add more E, it's reacting more, which means there's plenty of HBr to actually react. Okay? Okay. Different element, L in the same row of the periodic table. So in other words, we have L and then E in the same row. Okay? L with half the atomic mass. Okay? Is the atomic radius of L equal, less, or greater than the atomic radius of E? The answer is greater than. Lead with that. Okay? It's greater than. So the reasoning here, a couple ways you could have gone with this, but key is they're in the same row, which means they have the same energy level. So N, the N value, right? N equals the same value. So whether it's, row 2, row 3, whatever, we'll say N equals 3. That's fine. They're both in the same energy level. They have the same number of rings, okay? So that's the first piece. Within this, okay, E is bigger. In other words, it has more protons and electrons, okay? More protons and more electrons are going to attract more. So it's actually going to, the nucleus of E is going to suck in the electron shell more and create it smaller, right? So L is going to be bigger than E because its nucleus is less charged, right? This one has a bigger positive nucleus. It's going to draw in the electrons more. So that's really what we were looking for there, okay? Is that it has, L has fewer protons in the nucleus to attract those outermost electrons, resulting in a larger radius. Okay, so that's really what we were looking for that one. Okay, for E, you're given a data table here, and they say justify. You have to use that data to justify your answer to get full credit. So some of you guys wrote some things that may have been true, but if you didn't cite from the radius data, you're not going to get full credit here, okay? Okay, so I know we haven't talked a lot about lattice energy, but it gives you the definition, okay? It's defined as the energy required to separate an ionic solid into different ions, okay? So here's what we were looking for you to say, okay? Is it going to be equal or less than, equal to, or greater than? So I'm going to say greater, period. Now here's my justification, okay? If the radius of M is smaller, okay, so M's radius is smaller, that means that the MO lattice, right, so you're going to have MO, 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 right? You're going to have this big lattice of this ionic compound stuck together, right, with these ions packed in. If the radius of M is so small, these are going to be closer together, right? And so if they're closer together, they're going to be attracted to each other more and harder to pull apart. And lattice energy is the amount of energy required to pull them apart. So if they have a smaller, if M has a smaller radius, they're going to be more tightly packed, therefore going to require more energy to pull them apart. So that was the key that we were looking for there. The other thing you could have said, and some of you did, which is if its radius is smaller, that means the nucleus of M is going to actually be closer to the electron cloud of the oxygen in this case, therefore attracting that. Also totally cool to say. But you had to cite something about the radius in order to get full credit there. Okay. And then let's see the last one here. First one was just a quick Lewis structure, so you should have gotten a triple bond here between the carbons. Which of the four molecules contains the shortest carbon-to-carbon bond? That's going to be, I forgot the carbon. That's going to be the ethyne, because a triple bond is shorter than a single bond, which is what all the other ones were. Okay? And then the last one is going to be, what's the shape around each of these carbons, X and Y? So the shape around carbon X is going to be trigonoplanar because it's sp2 hybridized. Y is going to be tetrahedral because it's sp3 hybridized. Though I don't even think it asked you for Y. I think it just said you had to list that. So trigonoplanar, planar, and then tetrahedral. Okay? Okay. Energy is required to boil ethanol. Consider the statement. As it boils, energy goes into breaking the bonds. Is this true or false? This is the key word in the entire thing. This is false. Okay? Boiling is a physical change. There are no bonds being broken here. Okay? The only thing being broken is IMFs. IMFs are broken, not chemical bonds. Boiling is spreading out of the molecules. You are not changing the integrity of the substance. Okay, so that's a really, really, really key point. Okay, so it's not breaking bonds. Identify a compound from the table that is non-polar. Okay, so if we go back up to the table, okay, we're looking for something non-polar. Your best answers here are going to be either ethane or ethyne. Those are your best answers because they are exclusively carbon-to-carbon or carbon-to-hydrogen bonds. Those are always non-polar. Carbon-to-carbon, carbon-to-hydrogen, always non-polar bonds. Their difference in electronegativity is below the threshold. So that's your best answer. Either one of those would have been fine. And your justification is that C and H bonds are non-polar. Okay, and then the last one, ethanol is completely soluble in water, whereas ethanol has limited solubility in water. So explain your answer in terms of intermolecular force. That's key. Use intermolecular forces in your language to explain. So if we go back up to our image here, right, we're comparing the ethanol and the ethynyl. Okay, so the key here, they tell you ethanol is soluble in water. Again, like dissolves like. Ethanol has the ability here to hydrogen bond. So the intermolecular force that's present in ethanol is hydrogen bonding. If you look here, right, there is S to H does not allow for hydrogen bonding for that. So much weaker intermolecular forces there. This has, maybe a slight dipole, but not much. Okay. It does tell you it's slightly soluble in water, so I think that gives you a little bit of an inclination that it's slightly dipole, but for the most part, very much less intermolecular forces than the ethanol, therefore less soluble in water. So that is the answer to that one. I think that's it.